Hi everyone, so we're going to be looking at the collision theory and the rate of reaction. So let's see the collision theory. So this theory tries to explain the conditions that need to take place in order for a reaction to be successful, for a reaction to occur. If we consider this scene from the movie 300 as representing a reaction taking place, then a successful reaction would be where the enemy is killed. And for an enemy to be killed, there needs to be three things that happen. Firstly, the arrow should hit the enemy. Secondly, the arrow should hit the enemy at an appropriate area that is fatal to that person. And thirdly, the arrow should hit the enemy with enough force or enough energy for the killing to take place. So similarly, for a reaction to take place, the three conditions involve collision, orientation, and energy of the particles. So firstly, particles must collide. So as you can see here, collision should take place. And they must collide in the appropriate orientation. So as you can see here, you have appropriate orientation. And in this case, there is the orientation is not conductive to the reaction. So here you can see the reaction is not happening. So you don't have any new products being formed here. While here, the reaction is occurring in the proper orientation. And also, particles must collide with a certain minimum amount of energy. And if you still recall your IGCSE, this minimum amount of energy required for a reaction to take place is called the activation energy. Now, the more you are able to influence these conditions, the more you'll be able to influence how much products you are getting, right? So this is a successful reaction, and the second one is an unsuccessful collision, right? So anything that is able to increase the number of collisions is eventually going to increase the number of successful collisions. You can have, let's say, 1,000 collisions, and out of these 1,000 collisions, you can have only 30% that is going to be successful. So if you are able to increase the number of collisions, you're going to increase the number of successful collisions. So we're going to see all the different factors that can increase the number of collisions and hence increase the number of successful collisions. Let's see the activation energy. Now, activation energy, abbreviated EA, it's the minimum energy that colliding molecules need to possess in order to have a successful collision. That is going to lead to a reaction. Now, let's consider these two reactions. Here you have an endothermic reaction, and there you have an exothermic reaction. So this is the energy profile diagram for these two kinds of reaction. If you still remember your IGCSE, an exothermic reaction has delta H negative, which means that energy is liberated to the surroundings, and the products is going to have less energy than the reactants. And one very common example of an exothermic reaction is combustion. So here you can see the product have less energy than the reactant. So here there is a mistake. This is an exothermic reaction. Delta H is negative. Delta H goes from reactants to products. So it's not a double-sided arrow. It's just a single arrow pointing downwards. The delta H arrow always moves from reactant to product. Not a double-sided arrow, just one head arrow. And similarly, for an endothermic reaction, So you have energy absorbed from the surroundings, and the products here have more energy than the reactants. One example is photosynthesis, and similarly, the delta H arrows goes from the level of the reactants to the level of the products as a single arrow. The arrowhead is pointing on a single direction. So if we look at these two reactions, we can add the activation energy on the graph. The activation energy is always going to go from the level of the reactants, pointing towards the peak of the reaction. So the peak of the reaction is here. So it goes from the level of the reactants to the peak. This is activation energy. Again, for the exothermic reaction, it starts at the level of the reactants to the peak. So it points upwards. It points towards the peak. So this is activation energy. So when the activation energy is supplied to the reactants are going to reach a transition state. The TS here, it's achieved. And from the TS, from the transition state, we're going to be able to get the products. Now, the activation energy represents the energy barrier. So it's the energy barrier for the reaction to occur. And different reactions will have different activation energies.